No, I haven't done them. Fun.
Well, yeah. Let's do it. So, as far as the
That's some nice.
Yeah, sort of thermodynamics. Did you answer the first question in grant or actual dollars?
Okay, so let's get started. So what I want to do today is I want to finish off our discussion of the binomial distribution. So if you remember, we did kind of this silly problem where we imagined a drunk trying to walk home, and they could either step to the left or to the right. Maybe we count as a successful step steps to the right. So what's the probability of X steps to the right out of a total of N steps when the probability of one step being to the right is P? And so it's given by this thing. We worked out some properties of the binomial distribution. For example, the mean is given by N times P. We didn't do this calculation, but I will do a version of it today. We wrote down that sigma squared is NP times 1 minus P. So an easy way to remember this actually is the number of steps times the probability of success times the probability of failure. So they usually, when talking about binomial distributions, if P is probability of success, then they use Q for the probability of failure, but Q is just 1 minus P. So it's NPQ if you want. So what I want to do is I want to push this a little bit further. We'll still be talking about the drunk. But then at the end, what I'm going to hopefully be able to do is relate this back to an actual physics problem. So that's the goal. Let's see what happens. So let's try to calculate the mean displacement. And so for mean displacement, I'll use this notation. Delta X will be the displacement, and I'll use these angle brackets for the mean. And the mean of the square of the displacement. And so for that, we'll use our displacement is delta X, so we'll just square it, and then we take the average. What we're going to expect to find is that this should be 0 if we set the probability of stepping to the right to be 1/2, and then this will be some non-zero results. Okay, what we're going to try to do in the end is relate this to the Brownian motion lab that we have. Okay, so if we take x steps to the right, x steps to the right, the displacement to the right will be, let's call it delta x to the right. It's just going to be x times, say, L, where L is the size of one step, where L is the average step size. Right, so even if we call L the average step size, then we don't even have to require all steps to be exactly the same size. There's just some average step size. And if X is large enough, this will give us a good estimate of the true displacement. Okay, good. So likewise, there will be a displacement to the left will be, so delta x to the left. So if we took x steps to the right out of a total of n steps, that means there's n minus x steps to the left. And then they have the same average step size of L. Okay, so then what we want is the total final displacement. And so the net displacement, say delta x, is going to be the displacement to the right minus the displacement to the left. Okay, and so that's going to be, let's see, it's going to be xl minus xl. So we'll have a 2xl minus nl. And so we could write that as 2x minus n times l. All right, and so this makes sense because if x is equal to n by 2, half the steps were, say, to the right, then 2x is just going to be n, and we'd have n minus n is 0, and our net displacement would be 0. So that seems to make sense. Okay. We're going to calculate the average value of delta x. We're also going to calculate eventually the average value of delta x squared. And so let's just write out delta x squared right now. It's going to be a 4x squared minus 4nx plus n squared. N squared, all multiplied by L squared. So we're going to find the averages of both of these quantities. So that's the goal. All right, before we do the calculation, let me just remind you of a few things. So for a probability distribution of, say, I don't know, P of xj, where xj are the possible outcomes of some kind of measurement, we said that the average value of x was given by the sum of j equals 0 to n xj p of xj. The average of x squared would be the sum of j equals 0 to n of xj squared p of xj. And we could continue this. In fact, we could write any function of xj has an average value of that function times the probability and then evaluate the sum. So in general, any function f of xj has an average of, let's see, f of xj averaged would be the sum, well, okay, let me just say the average of f of x would be the sum j equals 0 to n. So it would be just f of xj times P of xj. This makes sense, right? Like our function could be x squared, and then we're just gonna get this x squared relationship. So what we'll do is we'll put in our expressions for the displacement delta x and the square of the displacement here and do those calculations. All right. So let's start with an easy one. So let's start with finding the average of delta x. So the average of delta x is going to be equal to, let's see, we're going to have a sum. We'll put the limits of the sum in a second, but we're just going to put delta x and times it by the probability distribution. And for us, our probability distribution is the binomial distribution. And let's see, we have possible values of x. So these are the number of successes when we do n trials, and the probability of any particular trial being successful is little p. Okay, and then let's just put in the limits here. We said we have to sum over all the possible outcomes. And so if we take n steps, one possible outcome is that none of those steps are to the right. So it's possible that x will be 0, but you could have one step or two of the steps to the right, or you could have all n of the steps being to the right. And so the possible outcomes are x's anywhere from 0 to n. Okay, and then we just have to do this calculation. Delta x, let's just remind ourselves what delta x was. 2x minus n times L. So we're going to just put that in there. This would be the sum of x equals 0 to n. Delta x is 2x minus n times L. Then we have our probability distribution. And so I'll just leave it like that. And so this is actually going to be pretty easy because we already know a few things about binomial distributions. So I'm going to rearrange how I write this. This could likewise be written as, let's see, we have 2L times x. 2L are constants, they can come outside the sum. So we have 2L, the sum of x equals 0 to n of x times this probability distribution. And then we have, let's see, minus n and L are both constants. And so those can both come out. And then we have the sum of x equals 0 to n. And it's just that probability distribution. What is this sum?
1.
Yeah. Sum over the probability of all the possible outcomes. It has to be one, something has to happen. What's this sum? It's the average of x, and for a binomial distribution, the average of x was equal to, if I take NP, that's right. So if I do run n experiments and the probability of each trial being successful is p, then n times p of them will on average be successful. Okay, and so that means that our average of delta x is equal to 2L NP minus NL. And so we can factor out, let's see, an NL we could factor out. So it would be 2P minus 1 times NL. And that is our average of delta x. Now, for someone who's really plastered, if P is 1/2, then there's no preference of stepping in one direction or the other. We get 2 times 1/2 is 1 minus 1 is 0. So we get the expected result of delta x is equal to 0 if P is equal to 1/2 as expected. Okay, good. So what I want to do then is see what happens if we try to calculate the average of the square of the displacement. So now let's find the average of delta x squared. Okay, so the average of delta x squared is going to be what? It's the sum of x equals 0 to n. All right, now we have to go back and see what delta x squared was, because I don't remember. Oh, okay, it's pretty complicated. I can't remember 3 terms in my head. So let's copy this. Okay, so there it is. That's delta x squared. Oops. And then we have to multiply by our probability distribution. That's all we have to do. Okay, let's see. What are we going to do? So we're going to have 4L squared and then the sum of x squared times PB. So it's going to be 4L squared sum of x squared times the binomial distribution minus 4NL squared sum of x equals 0 to n of x times the probability distribution. And then we have plus, maybe I can squeeze it in there, plus n squared L squared sum of the probability distribution from x equals 0 to n. All right. So we already dealt with things like this. We said this was just going to be n times p. And we said this was just going to be a 1. And so what we're left with is delta x squared average is 4L squared. This first sum is something we haven't tackled yet. And so we're going to have to do some work on that. But then we have minus, let's see, 4n squared p L squared is 4n squared p L squared plus n squared L squared. All right, hopefully that's right. Let's see if we're on track here. N squared p L squared. Yeah, I think so. I think we're okay. All right, so for the next little bit, what we're going to do is we're going to focus on evaluating the sum. If you remember last time, I said that you might have to do like some homework problem. This is kind of what I thought would be part of your homework, but I think we're going to do it because I want to get the results for this class. So let's focus now on evaluating. And it's useful to go through this because we'll see, some methods that we can use to manipulate these sorts of sums. All right. The first thing I'm going to do is I'm going to separate this out into the x equals 0 term plus the same sum, but starting from x equals 1. Okay, so this is equal to, it's kind of a weird thing. We could do 0 squared plus, 0 squared. And then this would be the PB for x equals 0 plus the sum of x equals 1 to n of x squared. Right. We did the same trick last class when we were calculating the sum for just x times PB. And so, of course, 0 squared times the probability distribution is just going to be 0. So that doesn't contribute anything.
If we were writing this on an exam, say, would we have to specify that step, or could we just go right to that?
Well, I mean, I think if you make it easier on the grader, just to make some indication that you're dropping the first term. So you don't have to write it out like this, but maybe leave a note so that people could understand. All right. So what we're calculating is the average of x squared. And so now it's the sum starting from x equals 1. And what we're going to do is I'll actually write out the binomial distribution now. So it's n factorial. Let's see if we can remember it. X factorial, n minus x factorial, p to the x, and then 1 minus p to the n minus x. All right. So we're gonna make some simplifications. The changes I'm gonna make are, one, I'm gonna write x squared over x factorial is the same as x squared over x times x minus one factorial. And then we can cancel one factor of x. And so that's just gonna be x over x minus one factorial. Okay, so that's one change we're gonna make. Another change that we're gonna make is I'm gonna write n factorial times p to the x is the same thing as n times n minus one factorial times p to the x minus one, which is the same thing as np n minus one factorial p to the x minus one. This is also the exact same step that we did last time. Okay, so then we sub these things in there, and what are we going to be left with? So we're doing the average of x squared. So we're going to get an NP. Those are both constants. I'm just going to take them outside the sum. So we'll have a NP will be sitting here. Sum of x equals 1 to n. And then let's see. The x squared just becomes an x. So we'll have an x. The n factorial became an n minus 1 factorial. N minus 1 factorial. And in the denominator, I think we should have an x minus 1 factorial. And then there's probably an n minus x factorial that hasn't changed. This is going to be p now to the x minus 1. And then we have 1 minus p to the n minus x. All right. So far, this is all the same steps we did last time. What's different is last time, this x would have been gone by now because we had an x instead of an x squared. But it's still there now. We have one factor of x left over. All right. We're still going to make the same steps as last time. We're going to sub in. Let's see. I want to sub in y is equal to x minus 1. Therefore, x is equal to y plus 1. When x equals 1, y equals 0. When x is equal to n, y is equal to n minus 1. Okay. So we're going to make that substitution. And let's see, what are we going to be left with? The average of x squared. NP doesn't change. The sum is now going to be a sum over y. And it's going to start from y equals 0 and go to n minus 1. So this is y equals 0 to n minus 1. So now here's where we're going to get a bit of a change. We have an x here. I'm going to write that as y plus 1. So that first x becomes a y plus 1. N minus 1 factorial. Nothing happens there. Denominator. X minus 1 is y. And then we have a n minus x, but minus x is minus y minus 1. So I'm going to write that as n minus 1 minus y. N minus 1 minus y, and that's a factorial. And then we have p to the x minus 1, but that's just a y, and 1 minus p to the n minus 1 minus y, n minus 1 minus y. Okay, I think that's all probably correct. So we're getting close to where we want to be. The remaining step is now to sub in. This is again, we also did this substitution before. M is n minus 1. So this is going to be an m, that's going to be an m, that's going to be an m, that's going to be an m. Otherwise, I'm not making any other changes. So the average of x squared is equal to np, sum of y equals 0 to m of y plus 1, that doesn't change. Then we have m factorial. This is y factorial. M minus y factorial, p to the y, 1 minus p to the m minus y, right? So n minus 1 becomes m. Now. This is a good situation because this is exactly the definition of the binomial distribution. It's just instead of being in terms of X and N, it's in terms of Y and M. Okay, so this is the binomial distribution for Y successes in M trials where the probability of success is P. Okay, so then now we're quite close to where we want to be. So we have NP times the sum Y equals 0 to M of Y plus 1 times this binomial distribution. And I'm going to emphasize that these are in terms of Y and M now. So then this is NP, let's see, sum Y equals 0 to M of Y, PB, Y, M, P, plus the sum of Y equals 0 to M of just 1 times the probability distribution. So it's just the sum of the probability distribution. Okay, good. And then close my brackets. All right. We've done this a bunch of times. Sum over probability distribution is just 1. What is this one going to give us? The average of Y, right, exactly. And the average of Y is equal to what? Yeah, so the average of X was what? It was N times P. So what would the average of Y have to be? M times P, that's exactly right. And so that's an important distinction, that this is now an M, because this is now recast as a binomial distribution out of M possible trials, not N. But M, if we go back and look, M is just N minus 1. So we can go back here and say, well, that's just N minus 1 times P. And so then finally, our average of X squared is now, let's see, NP times N minus 1 times P plus 1. And so it's some complicated thing. Let's see, what's it going to boil down to if we expand all this stuff? NP times NP. So this is going to be N squared P squared minus N times P. So it's minus NP squared plus NP. Okay, so that's our average of X squared. So that's the kind of calculation that you were going to be doing in your homework. But so this has all been like a big, huge aside, because what we were trying to do is, where the hell was it? This thing. We were trying to do this calculation. And I'm definitely not going to remember that. So you come with me. Okay, whoops. So that, so therefore, our results for the average of the square of displacement is, right, so remember delta X we're using for displacement. And we have to be careful because for little x we're using is the number of steps to the right, remember. So just to emphasize that. Okay, so all we're going to do is we're going to say, look, this thing is just the average of X squared, and now we have a result for that. And so we should be able to combine all these terms. And let's see what we get. Delta X squared average is equal to 4L squared times all of the stuff in the box there. N squared P squared minus NP squared plus NP minus. I'm gonna put the 4L squared because that's kind of looking like a common sort of factor. 4L squared, n squared p. And then it's plus, I'll write it as 4L squared, and then I'll write it as n squared over 4. Okay, so the 4's cancel, but this will let me factor out common 4L squared. And so this is equal to 4L squared. And what do we got? N squared p squared minus np squared plus np minus n squared p plus n squared over 4. I think there should be 5 terms. 1, 2, 3, 4, 5. 5 terms, and none of them cancel. It's kind of a funny thing, right? We have different combinations of powers of p and n. Let me see if I actually got this correct. 4L squared, n squared p squared minus np squared plus np minus n squared. Oh, good. Right, finally something to feel good about. Okay, so therefore delta x squared average is equal all this. This is the general result for the average of the square of the displacement. And this result holds for any value of p we want to choose. And you know, it's pretty complicated, right? It's pretty ugly little mess here. And so what I want to do is I want to consider a special case. And the case I want to consider is p is equal to 1/2. We'll consider that case because it's going to simplify this, but it's also the most interesting one. Because if we want to relate this back to Brownian motion, an assumption of Brownian motion is that you have some particles suspended in a fluid and it goes through collisions with the atoms in the fluid. And when it goes through, experiences those collisions, its direction is randomized. And so there's no preference for any particular direction. And if we have a 1D problem, that means moving left or right is equal. Equal chances of moving left or right for each scattering event. Of course, if you do a 2D or 3D version of that problem, in 2Ds, it can move in any direction in a plane. In 3D, it can move in any direction in, you know, some volume of space. Okay, let's consider the special case of P is 1/2. Okay, so what's going to happen here? Delta x squared average is going to be 4L squared. Okay, n squared times p squared is going to be n squared over 4. Minus n times p squared is going to be n over 4. Plus n times p is going to be n over 2. Minus n squared p is going to be n squared over 2. And then plus n squared over 4, that doesn't change. All right. If we did this right, there should be a whole lot of cancellation. Let's see, n squared over 4, n squared over 4, those combine to be n squared over 2, cancels with minus n squared over 2. Okay, so that and that and that cancel. Okay, good. And so then average of delta x squared is equal to, let's see, n over 2 minus n over 4 is plus n over 4. And so it's 4L squared, n over 4, 4's cancel, and so it's just nL squared. What a nice simple result after a pretty long calculation. So the result is that while the average displacement is 0 when p is 1/2, the average square of the displacement is not 0. And of course, you could have guessed that it would not be 0 because when we square displacements, we're always gonna get positive numbers. And so this is like averaging a bunch of positive numbers. It can't possibly be zero. But here's the actual result. And so the average of the square of the displacement is non-zero and proportional to n, which is just the number of steps taken. The number of steps taken. We could combine all these things and we could say, remember, the standard deviation was given by the average of the square minus the square of the average. I need my delta in there.
That'd be delta 36 squared.
Yes, it should be. That's right. So I could do it this way, right? You're right. But we know that this is going to be 0 for p is 1/2. And so that means the standard deviation is equal to just the square root of this thing. So it's root n times L, where L is the average step size. So if we had our drunk and they were, 10 steps away from their home, right? So they needed to try to take 10 steps to the right in order to get home. On average, their displacement is 0, but the standard deviation tells us kind of the distance or the length that they sort of sample. And we need this to get to 10L. And so it tells us that the drunk would, on average, have to take 100 steps to sample a space that's big enough to get 10 steps towards its home. And so, if you're 100 steps away, then you have to take 10,000 steps in order to have a chance of seeing your house. Okay, good. So if the drunk needs to take, say, 10 steps right to get home, on average, we'll need a total, of 100 steps to sample the required space. This is also true of when you put, I'm sure you've all seen this, right? You take a clear thing of water and you put like 1 drop of food coloring in it, and then you see it kind of diffuses out, right? And so those little colored particles that you put in the suspension, they're doing exactly this kind of random walk. It's just in 3 dimensions. And so you'll see it's always dark in the center, but it takes some time before it starts diffusing out. And they have to go through n² scattering events in order to reach a radius of n steps away from the center where you deposited this little food coloring drop. All right, good. So what I want to do is I want to see if we can connect this back to a real physics problem. Okay. And so, like I said, it's going to be this Brownian motion type argument. So, in fact, let's return to delta x² average was NL². Okay, so this result also applies to the Brownian motion of a particle suspended in a fluid. And so this is the result for its average square of displacement in the x direction. We could go through and we could do this calculation for delta y squared, and it would be exactly the same. We could do this calculation for delta z squared, and it would be exactly the same. And so if we wanted the actual entire average displacement in any given direction, it would be delta x squared plus delta y squared plus delta z squared. So there'd just be like a factor of 3 in front of here. So this is specifically for the x direction. And so if we think about our Brownian motion, what we would have is a particle, and then, you know, it undergoes some kind of scattering event. It hits it's bumped by some molecules in the solution, and it ends up over here, and then it scatters again, and again, and again, and again, again, and again. And it just bounces around here, and every time it's scattered, its direction is randomized, and, you know, maybe there's various distances that it scatters through, but there's some average distance that it scatters through, and we're going to represent that by L. Okay, so here, L is the average distance traveled by our particle between scattering events. This L is called the mean free path. L is called the mean free path. Whoops. Mean free path. Okay, good. You could also say, well, the particle has some average velocity. Its average velocity would be determined in part by the temperature of the solution, because the particles have thermal energy of kBt that determines, you know, their kinetic energy, how fast they're moving. And so if we know like some average time between scattering events, or actually, no, if we know, like, say, their average speed, and we know the average distance they travel between scattering events, we could calculate the average time between scattering events. So if the average time between scattering, between scattering events is tau, then the total time for n scatters is, or will be, t is n times tau. And so what I'm going to do is, in our result for delta x squared average, I'm going to write n as this total time t divided by tau. And so therefore, n is the total time t divided by tau. So this is total time. And that means delta x squared average is equal to, let's see, L squared times n. So it's t L squared over tau. Okay. The last thing that we're going to do is, it's pretty common for people to define a so-called diffusion coefficient. And a diffusion coefficient would determine, for example, when you put that food coloring in the middle of the clear fluid, like how quickly does that spherical color surface propagate out, is determined by a diffusion coefficient. So it is common to define a diffusion coefficient coefficient. And so that's given the symbol D. And the way it's defined is L squared over 2 tau. So that makes this L squared over tau is equal to just 2D. And if we do that, then this delta x squared average is 2D times T. Now, if you have done the Brownian motion experiment, or if you do it at some point during the 232 labs, when you read the manual, you actually get a result that's sort of like this. You calculate the average square of the displacement, and it's proportional to how long you wait, the time t, and then there's some prefactors. And for a spherical particle suspended in a fluid, you could actually calculate what this D should look like. And we're not going to do it, but if you read the manual for the Brownian motion lab, you will it works through all of those details. So this is the average displacement of the suspended particle in one dimension after a time t. So during this time interval t, the particle has gone through many scattering events, and the average distance that it'll move in one dimension is t times twice this diffusion coefficient. So for a spherical particle suspended in a fluid, the diffusion coefficient can be calculated, and it is given by the following. So D. So what it depends on is, it depends on the radius of the sphere, and it depends on the viscosity of the fluid, and it depends on the temperature of the system. So it is Boltzmann's constant times T over 6 pi eta times A. So here T is the temperature. The reason the temperature is relevant is because if we had a hotter fluid, then our little particle would have more thermal energy and it would be bouncing around a little more vigorously. And it makes sense that T is in the numerator, because higher temperatures is more thermal energy, and so our displacement would grow, our square of our displacement would grow. Eta is the viscosity of our fluid. It makes sense that it's in the denominator, because if we have like a really viscous fluid, like, you know, a particle suspended in ketchup or something like that, then, you know, it's not going to move around much compared to if it's in like some really kind of alcohol, which is not very viscous. Okay, and then A is the particle radius. And again, it makes sense that a fat particle with a large radius wouldn't move as much as a small little particle. All right, this Boltzmann's constant, you could always write in terms of Avogadro's number and the gas constant. And so you could write this as RT over 6 pi eta Avogadro's number times A. And so that means our delta x squared is 2 times this diffusion coefficient times T. So it's 2R temperature, 6 pi eta Avogadro's constant A, and then we have to multiply by T. So the 2 over 6 you could write as a 1/3 if you wanted. But the important point is what people do in this Brownian motion experiment is you measure this, you actually watch the particles, you make a recording of the particles, and then you actually measure the average value of the square of the displacement for different time intervals t. And so that should be a linear set of data. So if we were to plot delta x squared averaged as a function of how long you wait, you should get a linear set of data. And if you put a straight line through it, this slope well, let's not use m, we used m before earlier in the notes. The slope is equal to 2RT over 6 pi eta NA, Avogadro's number times 8. And so you could solve for Avogadro's number. And all the other stuff, you know, if you know your particle size, you know the viscosity of the fluid you're using, and you know the temperature, then the slope is all you need to find Avogadro's number. Okay, good. And so I think it's kind of neat that, you know, kind of the silly problem a drunk trying to stumble home is essentially completely analogous to our random walk of our particle in a suspended fluid. This was, all these details were worked out by Einstein. Einstein had his so-called miracle year, I think it was 1905, where I think he published, I think it was 3 or 4 results that were all probably worthy of Nobel Prizes. I think in 1905, he did the Brownian motion stuff, he did photoelectric effect, and he did special relativity. Maybe there's another one that I'm forgetting. So any one of those you probably could have given a Nobel Prize for, all in 1 year. I believe it's actually the Brownian motion stuff that he got. No, it was photoelectric effect. Okay, yeah. Did anyone know, was there 4 results in the miracle year or just 3? It was.
And then the percentage square was out.
Let's just see. Let's go. Miracle year.
Brownian motion through pieces into the
Yeah, well, what does Wikipedia say? There are 4 papers, so there are 4. The first paper was photoelectric, second was Brownian motion, third was special relativity, so that I got. Oh yeah, and then you're right, it is the E equals MC squared is the other one. Yep, okay, anyways, that's it. So thank you very much. Have a good weekend. I will work out an assignment for the binomial distribution, and I'll get that posted